Part 3, practice test, multiple choice explanation. I'm starting with question 11 to avoid the other questions don't have to do with part 3. I'll go over those later, getting ready for the semester exam. So, number 11, two factors, effectiveness of for evaluating the effectiveness of commercial. The time length and the format. There's 3 levels for the time length factor and 2 levels for the format factor. For a total number of treatments, which is the product of the numbers of the levels. So the total number of treatments is going to equal 3 times 2. This is the multiplication counting principle when you have a number of choices. So anyway, subjects are randomly assigned to either viewing a 15-second live or a 15-second animated or a 30-second live or a 30-second animated or a 60-second live or a 60-second animated commercial. So if there were 3 factors, then you'd have with 2 levels, then you'd have 3 times 2 times 2 for a total of 12 treatments. So then at the end you compare the results. So that's number 11. So the right answer is A. Let's go through B. In B, the number of levels of the 2 factors is added to make 5 treatments. Well, that doesn't make sense. There's 6 total combinations of the when you combine it together, when you multiply 3 times 2. C, there's no blocking. If you block, you're eliminating that variable as something that you're going to learn about, and in fact they want the levels to be a factor in the treatment. So there's no blocking, and there's certainly not just 2 questions and 1 response, and it's not a survey. And it's not a sample. Okay, it's an experiment. So D and E are wrong because it's not a survey. Okay, it is an experiment. Number 12. So, doing research, school newspaper regarding the students' perceptions about security guards. Okay, so he's worried about undercoverage bias created by chronically truant students. His concern is A, unwarranted. Well, no, that's wrong. If enough students refuse to participate, there is non-response bias. B, justified because chronically truant students will be difficult to survey. Not surveying a specific part of the population is undercoverage, so B is right. C, wrong. Unwarranted because students who cannot be surveyed are not part of the population of interest. The population of interest is all students, including those who are chronically truant. D, unwarranted because students who cannot be surveyed are not part of the sample. That's wrong. The sample cannot redeem a flawed survey. Just because somebody isn't in it doesn't mean the sample is okay. And E, justified because people need to be forced. That's wrong. Forcing answers is a form of response bias. 13. A poll of 500 randomly selected likely voters. Now, there's a problem with this question, which it didn't become clear to me until I went over this in much more detail in answering it myself. So let's lay it out. Simulation of poll based on the belief that 47% support for candidate A. This is for the opposition, who believes only 47% like him. So you're going to run a bunch of simulations and see if it's believable that actually 51% support candidate A. So you run simulations, 200 trials of 500 voters, 0 to 46, they like A. 47 to 99, they don't like them. They generate all these pairs of numbers. You do this with technology, obviously. And what you end up with is 29 out of 200 trials are 51% or more. So there's about a 15% probability in the simulation that a simulation is 51% or more, assuming real support is 47%. Since 15% as a probability could easily occur randomly, the simulation does not provide evidence to reject the 51% poll statistic. Now, what I failed to do when I first investigated this question was look at what they're asking you. Is the opposition's claim that candidate A has support of only 47% of the likely voters plausible? Now, based on the correct answer, I have to make the decision that plausible is wrong and that it should say implausible or incorrect or something like that. Okay? Because, well, let's look at the answers and I'll explain why I have this view. So A, the average proportion of voters supporting candidate in the samples would be less than 51%. So a sample of proportion of 51% would be too unexpected. All right, well, that's wrong. The proportion of simulations of 51% or greater does not have to be less than 51% to reject the 51% statistic. To reject 51%, the proportion of simulations 51% or more must be less than 5%. The idea is, let's go back to here, 15% could easily occur randomly. So it's not ruled out as a possibility as being the true proportion, the population parameter, if you will, that 51% is the true proportion. 15% of the simulations could easily occur randomly. All right, so let's look at B. Now remember, we're not asking is the opposition's claim plausible. We're really asking is the opposition's claim implausible or incorrect. Okay, B, no, because the majority of sample proportions would be less than 51%. So a sample of proportion of 51% would be too unexpected under this model. Okay, really it's the same argument here. The fact that the majority of sample proportion is less than 51% is not proof that 51% is wrong. What matters is that 15% of the simulations of 51% or greater is not improbable. This is what you have to, this is how simulations are used to establish evidence for something. C. Okay, now remember, the question that we're answering is the opposition's claim incorrect? C. No, because only 29 of the 200 samples had a proportion of 51% or greater supporting candidate A. So a sample proportion of 51% would be too unexpected under this model. 29 out of 200 is not an unlikely occurrence. So C is very close to being the right answer, okay? Except that it's got the logic reversed, okay? The statement is wrong, okay? 29 out of 200 is not an unexpected result. Okay, D. Now remember, we're answering the question, is the opposition's claim incorrect that candidate A has a support of only 47%? Is it incorrect? D. Yes. Because 29 of the 200 samples had a proportion of 51% or greater supporting candidate A, so a sample proportion of 51% is plausible. Okay? All right. And that's the right answer. Let me look at the answers for, what is this, 13? Let's check the answers real quick for 13. 13, the answer is D. Okay, so I just have to make the assumption that the question was worded incorrectly, because all the answers, the way they're worded, fit the question being, is the opposition's claim that candidate A has the support of only 47% of the voters implausible? Okay, and then E, it's implausible, yes. Okay, now this is interesting. It's implausible, yes, because a sample proportion of 51% occurred more than once. So it's possible to get a sample proportion of 51% in this model. That's wrong. Simulation samples of 51% or greater must occur more than just twice for the 51% statistic to stand up. If only 2 simulations showed 51% or greater, that would be evidence to reject 51%, since 2 out of 200, or 1%, is unlikely to occur randomly. Okay, now remember, 5% is where our threshold of significance lies. And that's at 5% or less, we start thinking that something occurring randomly starts to seem somewhat unlikely. Okay, so that's 13. 14, playing with 10 people that on it, okay? Each ticket holder has a 10% chance of not showing up. So the airline sells 12 tickets for each flight. Which is an appropriate plan for a simulation that uses a table of random digits to estimate the probability that exactly 10 people show up for the flight? Notice the response variable. Do exactly 10 people show up? Okay. So the probability of a no-show is 0.1. 12 tickets are sold. So 0 we'll call a no-show. 1 to 9 is a show. Okay. Generate 12 random numbers repeating, representing 12 tickets. Count how many show, or how many are 1 to 9. If the shows exactly equals 10, they record a yes for this trial and then repeat. Now that's according to the directions that they gave. Now the answers don't, all the answers don't exactly fit this, but according to how I read this, the response variable is how often exactly 10 people show up. Okay, so let's look at A. Let digit pairs 01 to 12 represent the 12 tickets. In the table, select pairs of digits, ignoring repeats and pairs that do not represent a ticket. Continue until you get 10 seats filled. Record the number of pairs needed to get 10 seats filled. Well, wrong. The simulation tests how many times exactly 10 out of 12 people show up, not how many passengers are required to fill the 10 seats. Okay, if you're running the simulation the way it's described, you could theoretically have no seats filled. Or you could have 12 people show up. Okay, so you're not trying to fill the 10 seats. That's not what the thing is about. Okay, B, let digits 01 to 12 represent the 12 tickets. In the table, select pairs of digits until you find 10 pairs that represent tickets and record the proportion of trials required 10 or fewer. Wrong. The probability that a passenger shows up is 0.9. In this simulation, it is 12 out of 99, right? 01 to 12 are the 12 tickets. Select pairs of digits until you find 10 pairs represent tickets. Okay, so you're rejecting all these. You know, it doesn't say anything about rejecting the ones that are outside the range. So record the proportion of trials required 10 or fewer. And the response variable is wrong. The proportion of trials required 10 or fewer. Anyway, there's a lot of problems with B. C, let digit pairs 01 to 12 represent a seat that was filled and other pairs represent a seat that was not filled. In the table, select 10 pairs of digits, ignoring repeat, and record the number of seats that were filled. All right. Probability, again, is way off. The number of tickets sold is not 10, but 12. Okay, D. Let digit 0, okay, now we're getting on the right track, represent a seat that was filled, and 1 to 9 a seat that was not filled. Okay, that's the right probability. Okay, good start. In the table, select 10 digits and record the number of seats that were filled. Response variable is incomplete, although that's going to end up being sort of a non-issue. The response variable is whether or not exactly 10 passengers show. But, probably is correct, but 12 tickets are sold, not 10. Okay, 12 are sold, not 10. Is that the end of this page here? I think so. All right. So I go to the top of the next page, and we get E. Let digit 0 represent a ticket holder that doesn't show up, and 1 to 9 a ticket holder that shows up. Okay, probability is okay. Select 12 digits, and that's the number of tickets that are sold. And record the number of passengers who show up. Okay? Now again, you're only supposed to record, the response variable is supposed to be whether or not exactly 10 passengers show. So I'm not crazy about E, but E's the only one that could possibly be right. Okay, 15. Local news program decides to cut cables. See how they need about that. And they set up. Station gives one number to dial if you like the new format, and another number to dial if you don't like it. Which of the following is the correct characterization of the sampling approach? Okay, A, it's biased because people might dial the number incorrectly, and therefore everyone will not be correctly represented. Wrong. This is not under coverage. Under coverage, bias implies a flawed attempt to sample voluntary response. This is voluntary response. I ask viewers to call in. Not a random sample, voluntary response bias. That's what you're thinking ahead of time. So that's what you're looking for in your answers. B, the sampling approach will be biased because the people who call in will be those who have stronger feelings about the new format, and therefore the sample will not be representative of the population. Now notice, they don't tell you it's voluntary response bias, but that's what voluntary response bias means. Okay? C, the sampling approach will be unbiased because people can call in with either opinion. Therefore, the sample will be representative of the population. The sample, see, that's wrong. I didn't write down wrong. The sample must be random to represent the population. There's no randomness in the population in the sample. It's not a sample at all. D, the sampling approach will be unbiased because the station doesn't know who will call in, making it a random sample. Anonymity has nothing to do with random selection of subjects. This is the colloquial meaning of random, as in some random person called in or walked in or some random thing happened, which means almost exactly the opposite of what true randomness is. E, it is impossible to tell whether the sampling approach will be biased or not because the station can't predict who will call in. If a sampling approach cannot be proven random, then it is definitely biased. So E is wrong. 16. We're going to add, city is going to add roundabouts, okay? And they want to have a phone survey. So, many people object to the city's plan to reduce the unnecessary accidents. All right, right there. Okay, reduce unnecessary accidents, response bias. Okay. Now that's of one kind, encouraging people to answer one way. And then into strange European-style roundabouts, response bias. Many people object, response bias. Do you object, response bias? And then finally, there's convenience bias. He's calling people on his lunch break with undercoverage. So we're going to quickly see A, B, C, D. They're all correct. Okay? So A talks about the convenience bias, undercoverage, and all the others, B, C, and D, talk about oh, I went to the wrong, I messed up here. Here, let's see. And D, all state the other forms of response bias, and then so E is the correct answer. All are possible sources of bias in the survey. All right, 17, differences between experiments and observational studies. A, response variable in an experiment, but not in an observational study. That is totally wrong. Okay, observational studies always have response variables. B, there is at least one explanatory variable in an experiment, but not in an observational study. That's wrong. Both observational studies and experiments are seeking explanations, which means they are looking at both explanatory variables and consequential variables or response variables, factors, if you will. The only thing is the study can't establish cause and effect. C, an experiment requires blocking while observation study does not. Okay, you do not have to have blocking to have an experiment. It's a good thing to have if you want to get rid of possible sources of confounding, but it is not required. D, an experiment can be used to establish a causal relationship, but an observational study cannot. That is correct enough for our course. E, observational studies require larger samples than experiments. That's wrong. Observational studies can focus on just a few subjects. Okay. 18, the stats teachers and the topic sequence. Okay, so here's what they're talking about. They're going to pick teachers with two groups of two stats sections, and then have them randomly select the class to get either data analysis first and then design, or vice versa. Okay, so there's definitely blocking in this experiment because they're blocked by teachers. In other words, the teachers are chosen specifically. So the classes are separated by teacher, and this is to remove the confounding variable of teacher expertise in the subject. So once the experiment is blocked by teacher, then classes are randomly assigned to the two different treatments, either design and then data analysis, or data analysis and then design. So the subjects are the classes. In other words, if you want to figure out who the subjects are, simply ask yourself this: who is getting assigned treatments? Whoever's getting assigned treatments are the subjects. Now, so in this case, it's not the individual students, but rather the entire class of the students. And what's the response variable? It's going to be the average AP test score for each class. So it's blocked by teacher to avoid confounding. The response variable is the difference in AP score for the two classes. Okay, so A is right. The experimental units are the classrooms. That's or the subjects or whatever, the experimental units. The blocks are the teachers. The response variable is the difference in average AP exam for each teacher's classes. Okay, B. The experimental units are the teachers. Wrong. The teachers are not being evaluated. Otherwise, they would be randomly assigned to treatments. The teachers are blocked to remove them and their differences from the experiment. C. The experimental units are the individual students. Wrong. If the students are the subjects, if the units are the students, they are not being randomly assigned to treatments. So something is seriously wrong. D, same thing. Okay, see above. Everything else in D is correct, but it's not going to work because there's nowhere in the design where individual students are assigned to treatments. And then E, the experimental units are the order of topics. No, that's the treatments. Okay, the order of topics is the treatment. All right, 19. 2, study by McGill University with cholesterol. Okay. So let's look at these two experiments. Let's do a little thinking about them. All right. Cholesterol and placebo. McGill randomly assigns people to get the probiotic or the placebo, and then they compare the results. In Britain is a matched pairs, and that the same subjects take the probiotic, and then a time later they take the placebo. Again, the results are compared. Okay, so let's go through the questions about this. I think now we're on the next page. All right, so which of the following is true? The McGill study is a controlled randomized experiment. That's true. While the British study is an observational study. That's false. The British study is an experiment. It's matched pairs. B, the McGill study is a completely randomized experiment, while the British study is matched pairs. That is correct. C, the results from the McGill study are more valid because it includes blinding, while the British study does not. The British study is blinded. They use a placebo, so there's no reason why it can't be blinded. D, remember, placebos are put in there for the purpose of blinding. the placebos are added to an experiment so it can be blinded as much as possible. D, we have reason to believe the design of one of these experiments is flawed since the results are contradictory. Wrong. Properly conducted experiments differ all the time. Remember, they're conducted on 2 different populations. So, all kinds of differences between the populations. Conclusions from the British study cannot be trusted since there's no control group. Wrong. A control group is not required for an experiment. All right. I think we got one more. 20. Okay. I didn't. Okay, here's 20. I forgot to do 20, so I just had to do it. Okay, so 20 starts out, in a Japanese study, researchers looked at. Okay, right away, that phrase, researchers looked at, tells you this is an observational study. The very phrase, subjects are not being assigned to treatments. They're simply looking at people with back pain who are in an aquatic exercise program. Okay, there are no set of subjects here that are being assigned randomly to treatments, so it is not an experiment. But it is an observational study, and in that sense, everything's fine, and certainly a lot can be learned from it. Okay, which of the following statements is true? A is wrong, not true. It's not an experiment. B, wrong, not an experiment. C, conclusions based on this observational study are suspect since participation in the aquatic program may be confounded with other lifestyle behaviors that may cause the improvement of lower back health. True. Confounding is always a problem with observational studies. D, conclusions based on this observational study are suspect since a sample size of 35 is too small. Wrong, 35 is not an unusually small sample size. E, the study is not an observational study since the aquatic program is a treatment. Wrong, subjects were not randomly assigned to the treatments. It's not an experiment. And that's it.